First of all, I want to thank the organizers for organizing this nice event. I will be talking about eigenstate correlations across localization transition in non-Hermitian systems. So this is a work I was doing with Manas and Sitodi here. So before going into the details, let's talk about localization in quantum systems. So we know that if we have a clean system with periodic potentials, then the eigenstates are block states, which are normally extended to the whole system. Now, Anderson asked this question that if instead of periodic potential, we had a random disordered potential. So it turns out that in very strong in presence of strong random disordered potentials, eigenstates becomes exponentially localized. So by that I mean it becomes exponentially localized at particular sites of the system, and the wave function amplitude falls off exponentially as one goes far away from this site. Now, generally, the effect of interaction on these localizing systems was tried, and it turns out in one dimensional at least. So it is now well understood that there is a many-body localizing system. That means the in presence of strong enough disorder, interaction cannot restore conductivity in the system, and the system is still localized. So those are called many-body localized. Now, all these are closed quantum systems. But in general, systems are bound to be coupled with environments. If we want to do some measurement on a system, then the measuring apparatus will interact with the system. So in general, we should consider open systems instead of closed systems. So naturally, the question has been asked that whether localization survives in presence of this kind of couplings. So there are two paths for answering this question. So one path was coupling external baths with the strong many-body localizing systems and studying the effect of it. And there was another way of addressing this kind of questions is by introducing some non-Hermitian Hamiltonian, where this non-hermiticity parameter effectively represents the coupling with some environment. That means that there is a possibility of gain and loss coming out of the system from the environment, and that is contained in this non-Hermitian terms. So we will be concentrating on this path. So before going into non-Hermitian, let's talk about how localization transitions are studied. So in general, there are two ways. So by analyzing the eigenvalues and also the eigenstates. So when we analyze the eigenstates, if we see this kind of exponentially localized wave functions, we say that is localization. And when the wave functions are extended to the whole system, we say that is delocalized situation. Now, from the eigenvalues also, there is a way to understand whether these eigenstates are localized or not. And that is by studying the correlation of eigenvalues. So correlated eigenvalues actually means delocalization. That is because when there is delocalization, two wave functions can have a non-zero overlap. And when two wave functions have a non-zero overlap, their energies, if they are very nearby, they will, by the interaction of these two wave functions, they will have an opening of gap. So, so that will be a, but on the other hand, when we have exponentially localized, spatially localized wave functions in the system, that means when two wave functions are far apart and there is no overlap, they can have any energy they want, and thus there is no correlation between the eigenvalues. So when we see uncorrelated eigenvalues, that actually represents localization in the system. So today morning, Sparsh gave a talk where we were analyzing this kind of spectral properties of these eigenvalues. And from there, we were understanding whether there is localization or delocalization. So here I will be talking about eigenstates. Now, to understand the eigenstates, so we were talking about these exponentially localized states. Now, to quantify that, inverse participation ratio is one of the quantities, which actually is just a moment of the wave function amplitudes. So when I have a wave function which is extended to the whole system, then at a particular site, if I want to know what the amplitude of the wave function is, it will go as 1 by L. And if we and IPR is basically that probability raised to the power of 2, which is just another moment of that probability density of that wave function. coming from that wave function. And in case of, so basically IPR then scales. So by this IPR scaling, one can talk about how the eigenstates are localized in the system. And in case of a localized wave function, when this probability density is non-zero only on few sides, that means this probability density will be zero in other states. So when I sum over all the states, I should get some of the order of one number instead of system size dependency like this. And from there, one can analyze. So we can do the same thing for non-Hermitian systems as well. So for that, we just have to remember that non-Hermitian systems has this, I mean, when we want to diagonalize non-Hermitian systems, we get left and right eigenvectors. And in general, these left eigenvectors are not the Hermitian conjugate of right eigenvectors. And when we have in Hermitian systems this kind of orthogonality, we have a similar orthogonal, bi-orthogonal condition where these left and right eigenvectors are related. Now, one can again construct this kind of IPR kind of quantities by analyzing either the right eigenvector or the left eigenvector. And from there, one can talk about how the wave functions are localized in the system. Now, we won't be doing that as well. So we also notice that this left and right eigenvectors have this freedom that left eigenvectors for two different eigenvalues. So, okay, so I forgot to mention, so these eigenvalues are now complex since it is non-Hermitian. So corresponding to two separate eigenvalues, if we consider the two left eigenvectors, there can be a non-zero overlap. And similarly for the right eigenvectors. So what we consider here is a correlation quantity, which is O alpha beta, which is the overlap between this left and right eigenvectors for two eigenvalues, which are not the same. And so actually we define this quantity, which is actually resolved in the eigenvalue spacing in the complex plane. And so here, what we are mostly calculating is, so this omega is now the difference of the complex eigenvalues. And let's say omega is some mod omega e to the power I theta. And so we are integrating over all these thetas. So basically this quantity now depends only on the absolute value of the distance between the eigenvalues. And hence all these things becomes I mean, just a one parameter scaling, and it's easier to see. But we can also see the scaling of this quantity with the complex omega also. There is no problem in that. So, and just to remind, for Hermitian systems, since these are like this condition satisfied that left eigenvectors are Hermitian conjugate of the right eigenvectors. So these O alpha betas are delta alpha beta. And here, since we have alpha not equal to beta, so this quantity doesn't even exist for Hermitian systems. So this is a purely non-Hermitian property. Now here I'm discussing this quantity for a random matrix. So R is a random matrix, a random complex matrix where the real and imaginary both are some randomly chosen numbers. And by constructing this random matrix, one can calculate this thing. And it is known from this paper in 1998 that, I mean, they have analytical formula which actually shows that in the very small omega limit, this thing diverges with a power of q. And this is a numerical calculation that we have done to check that analytical formula, where this n is the matrix sizes. And we see clearly this mod omega to the power q. Now here is the model that we are considering. So here is the model that we are considering. So this is this is a random matrix again. So where there are two numbers. So the diagonal entries are random numbers with chosen from a uniform distribution of width 2w. And the off-diagonal elements of the matrix are considered from a uniform distribution of this varying weight, where the weight varies as we go along a row as this power. So as this m and n are further apart, so the width is also very small. And for this kind of model, there is a delocalization transition as one tunes this w or the power p of this power law fall of the width. So by tuning both the parameters, one can see a delocalization transition. So we fix our w at 3 and vary this p to see the transition in our calculation. So for this quantity, we calculate these eigenstate correlations. And so here we see for this p 0.5 in this regime, we indeed see this correspondence with the non-Hermitian random matrix behavior that we have seen. So this this thing diverges as a omega cube, and in the deep in the localized phase when p was 1, so we see a suppression in localization, and in some intermediate value p 0.7 we see some anomalous exponent for this quantity. So in the next slide, actually, we analyze these the slope of these curves for different system sizes, and as we vary the p. So this is a representation for a particular matrix size. So as we see, if we change the p, this slope gradually decreases, and by doing a system size analysis, we show that this exponent actually changes from 3 to 0. And we see a clear crossing as we increase the system size around p equal to 0.7. So before 0.7, the expectation is if we increase the system size, this exponent should go to 3, which is the non-Hermitian RMT limit. And after 0.7, if we increase the system size, this thing approaches the nu equal to 0 value, which we explain with some perturbative treatment. So using some perturbative treatment, we exactly calculate this thing in our analytical formula, and we get omega to the power mod 0 behavior, mod omega to the power 0 behavior. So which I am not discussing in this talk since, yeah. And this is the summary. So basically, to conclude that the behavior of eigenstate correlation is distinctly different in delocalized and localization transition. So this quantity can be used as a diagnostic to understand, and this also tells us about how the dynamics of the system will be, since there is this omega dependency of the quantity. And in the delocalized phase, the correlation corresponds to that of non-Hermitian, but in the deep localized phase, the correlations are suppressed, and this nu captures the localization transition. And thank you for your time.
Thanks for the wonderful talk. Do we have any questions? Yes, Luke.
So this, first of all, this 1 by mod omega cube behavior, is there some simple way of understanding in terms of some eigenvalue repulsion or something like that?
No, actually, this is not exactly eigenvalue repulsion. So if we want to calculate, want to study the eigenvalue repulsion, so there, so this thing goes as, so as we go in the small omega limit, the number of eigenvalues that are very nearby in non-Hermitian system reduces because of level repulsion. So that scales as mod omega cube. But this is like, so this is when we are very closely, close in the complex plane of the eigenvalues, the correlation is higher. So this is other way of that.
So this is some eigenvalue attraction, is that how should
this is not an attraction, this is basically this overlap quantity. So this L alpha, L beta, and R alpha, R beta. So basically, so closely spaced eigenvalues have eigenfunctions which have more overlaps. But that doesn't mean there is no level repulsion. So because level repulsion is also seen here, oh, sorry. So actually, if you see this mod omega to the power -3, after that this dip, and that depends on the system size. So that is because as I go on very small omega, I get very less complex number pairs that are there in the system because of the level repulsion. And so that also comes here, but this omega cube behavior is independent of the spectral properties of the eigenvalues.
Okay. If I may, what is the analog in the Hermitian matrix?
No, actually, there is no analog in the Hermitian matrix of this thing.
Okay.
So because of this thing, that when these off-diagonal elements are strictly 0 in Hermitian matrix. So there are some eigenvector correlations in Hermitian matrices. So what is studied there is, let's say this thing, I psi alpha raised to powers 2, so mod psi alpha I square, and some other psi beta I square, some other eigenvector. So basically the correlation of these amplitudes of wave function at different eigenvalues at the same site, and that correlation can be studied. That is related to something, this return probability. So, but this is not exactly, there is nothing analogous in the Hermitian system for this quantity. This is strictly non-Hermitian.
Okay, thank you.
Any other question? Okay, so let us thank the speaker.
Thank you. Thank you.